how river avulsion. Okay, perfect. How river avulsions work. And that's what you're seeing on the screen here in progress. I'm going to move this zoom thing a little bit. So this is the Rio Cauca River. It's flowing northeast. It's in Colombia. And in the center here, we have this large breakout zone, which we call a, got a little annotation on there, which we call a crevasse. And now this crevasse could capture a large portion of the flow of the lower Cauca River and reroute it elsewhere on the floodplain. So that's right, the process of a river avulsion. And so rivers move around all the time, right? We have single thread rivers, and this is the kind of movement that we maybe are more comfortable with, or at least more people know about the type of single thread meandering that rivers generally go through. Right, we have sort of bars. I'm going to see if I can get this annotation off the screen, UA. Can everyone see that? Anyways, we have sort of bars that you can see here, right, point bars, we have counterpoint bars, even chute channels. We have evidence on the screen here from above that this river has been sort of moving around the floodplain. Of course, this is what it looks like in time lapse. I should note that these time lapses have really become a main modality in our field, I would argue, and they're just incredible because we can see the dynamics at play. This, of course, is a meandering river. You can see specific features like neck cutoffs, right, where a portion of the river is pinching itself out of existence. But we can use this sort of movement on the floodplain we can use this movement on the floodplain to denote something called the channel belt, right? And this is the idea that there is some active area around the channel where its movement is sort of integrated through time, and that sits in context with the larger floodplain, um, where is in where the land gets inundated during flood stage. But of course, there's another sort of common modality of river types, right? We have braided rivers, which of course look a lot different than our meandering rivers, just in the sense that they have multiple threads, they have these big bars that are moving sort of chaotically, right? We have a little bit of overbanking deposits to the north there, but largely it's harder to see, I would argue, in this image um, the sort of evidence of recent past, right? Like in the meandering river, we had a lot of evidence of where the river was, maybe 10, 20 years ago. Here, it's a little bit harder to see. Of course, I'm a sedimentologist, so I like to draw lines around sediment like this. But just in character from above, these sorts of braided systems do look quite a bit different than meandering systems. And of course, we can define a channel belt for these rivers as well. This is the Brahmaputra River, one of the most famous braided rivers on Earth. We can also draw a channel belt here in the sense that this is where the river has moved through time. Of course, it's much more chaotic. The things like the bar turnover timescale is much faster, but largely it stays still within this channel belt. But what I want to talk about today, right, is that higher order of channel movement, which is actually avulsion or moving outside of the channel belt entirely. So we're going to watch this here. This is the Rio Isaburo. It's flowing off of the Andean thrust front in Bolivia, and it's flowing from left to right on your screen. And you're going to see an avulsion happen inside this little red circle as I play this. Okay, so we have the parent channel, which you can see up top. And then very quickly, about now, it captures the flow of a much smaller stream to the south and does something what we call annex it. So it annexes the avulsion, or it annexes the other channel and creates an avulsion. And you can imagine if you were living in this area to the south, this would be a big problem. Of course, this is a little bit more remote, but that's what an avulsion is, right? It's escaping the channel belt entirely. In the north, on this parent channel, you can see we have that meandering channel belt. But this is jumping outside of that, and that is a fundamentally different process. See if I can go next. So Avulsions are important not just because they sort of make for very pretty, satellite GIFs, but they create a large part of the stratigraphic record itself. This is some work I did in my master's, but it's really just to show um, avulsion stratigraphy. This is Middle Green River in Uinta Basin, Utah. You can see these isolated channel sand bodies here on the right, and that's evidence of river avulsion because from sort of a Waltherian framework, right? You have a channel and then it avulses away, and you get this background floodplain, which is um, this slope forming stuff in between. Um, Lake Uinta in the Eocene time was this really shallow lake, and there was this ramp style delta from the south. That's really what we're looking at here. But again, the thing to notice is that when you have floodplain and then it's sort of studded with different isolated channel sand bodies, this is a good indication that avulsion actually occurred. And so if we want to be able to understand the stratigraphic record, right, particularly I should say the alluvial stratigraphic record, which we of course do, but maybe not to the point of a true forward model, right, then we need to understand the generating mechanisms of alluvial stratigraphy, in this case, avulsion. So avulsions not only, right, generate stratigraphy, but unfortunately they can have massive consequences. Many of us might be familiar with this event itself. This is the Indus River, an image from August 2010. And the Indus is one of these rivers that birthed civilization, right? I mean, it goes back in human history thousands of years. Millions of people live by the Indus. And in this specific example, in 2010, what happened is that an avulsion event occurred. And as you can see, the northern arm of this river, it flooded an area the size of Connecticut. It killed 2,000 people and it displaced about 20 million. And that's because, of course, you can imagine the river as a sort of fire hose that's on, and then it gets cut in half. And so this incoherent sort of flow that has yet to channelize itself into the floodplain just starts going everywhere. And that's really what makes it disastrous. And also the fact that they're fairly hard to predict in sort of an earthquake sense. And so these are real legitimate natural disasters. But despite the risks here, we still don't understand, I would say, maybe much about the mechanism of avulsion, or at least we don't have maybe a good validation of the mechanisms of avulsion. So we're going to talk about three questions. One is simply where do river avulsions occur in the source to sink system? Secondly, what are the conditions that favor river avulsion, so that precede it? And of course, this debate goes back in our community. And three, when an avulsion occurs, where does it go and how does it get there? We're going to talk about river pathfinding post-avulsion. Okay, so to start this, I want to first talk about how you find evidence of river avulsion. So this is a GIF right here of the Sirdarya River. It's flowing into the last little part of the Aral Sea. But I want to sort of set the stage and say that, you know, we didn't have global time lapse information in the sense of global imagery time lapse in this dynamic way until about 2013. Google Earth Engine came out in 2010, but really by 2013 is when we first got to see every inch of the surface of the Earth throughout the Landsat era. And that allowed folks like myself, right, sedimentologists interested in active sedimentary systems, to not just look at the scaling from imagery, but the rates and the dynamism at play for these rivers. And so myself, but also many others in the lab I come from, but also other labs, well, we used this information to search for evidence of river avulsion. And that's because simply river avulsion is fairly rare, right? I mean, in general, the rule of thumb is about once every 1,000 years. And of course, I just told you we don't have a great way to predict it. And so that means that river avulsions may happen, but we only record them when it's a big enough event that it's sort of written through history, historical records, or we've gone back and we've been able to look at recent cores, right, throughout the Holocene. Um, so how do you find new examples or examples that may have been missed of river avulsion? Well, the first thing we do is we sort of select a region and a time span. There are places that we have good confidence that river avulsions should occur, meaning there are places where there's a lot of sort of tectonic activity, there's a lot of active subsidence, and they've been studied before in some places, right? Saskatchewan, the Koshi River, right? The Indus River, for example. So once you select a sort of region and time span, how this works is that we have a stack of images to work with. So let's say we select this Sir Daria region and we want to average over a year, right? Landsat takes about 23, 25 images in a single year. So we have that amount of images to work with. So for a single region, we can look through the images through time. And we can see the river in different conditions, right? It might be flooded, it might have clouds, might have more clouds. The seasons might change. But what we can do after about a year is remove all the errant or clouded pixels and simply take an average or a median, excuse me, through time of the good pixels. That gives us a composite, and then we just repeat each year and stack. And that process, which is a fairly simple remote sensing operation, again, really wasn't possible until the last decade. Which has allowed us to look and scour the surface of the Earth for examples of river avulsion. So using this methodology, again, myself, but also others, that come from my lab and elsewhere, have cataloged with sort of Landsat data avulsions that have started and completed between 1984 and 2022, and that's what you're seeing on the screen here. Notice I've broken these into three pretty basic categories. There's 174 examples here. I should say this is not a sort of comprehensive grid search estimate of all the avulsions on Earth. It is a pretty good compilation, I would say, looking over the vast majority of the surface of the Earth at larger rivers. But I don't want to represent that this is maybe the same as having some algorithm run through and search every pixel on Earth. But 174 examples is an N value that we're happy with, and I want to talk about the categories. So simply, deltaic rivers here are in blue. These are avulsions that occurred, on a delta. Fan is in orange. Again, fan is broad there. It includes alluvial, fluvial fans, anything near sort of the mountain front exit. And then everything in between, I've just called alluvial plain rivers. And this is just to give myself an idea of sort of what's the breakdown geomorphically of these systems. But we want to be able to compare something about these specific avulsions to one another in a source to sink framework. And so to do that, we had to come up with a normalized datum with which to compare these. So what does that mean? Essentially, if we know where an avulsion occurred, say it occurred, let me see if I can get the little laser pointer going here. Let's say it occurred sort of halfway along the river, right? This is a river that's sort of defined from the source to the sink. So if one occurred about halfway, what I did is trace the distance up the channel all the way to what I'm calling the mountain front exit. This is where the river leaves topographic confinement. It goes from confined to unconfined. And I can set that as 0 in my sort of datum, right? This is the start of the alluvial transport system or the end of that sort of source terrain. Then we can trace the river all the way back down to the delta where it enters a standing body of water. And that can be 1, or that can be the end of our sort of normalized datum. And in doing this, what we're able to do is place all of the rivers in a 0 to 1 space by where they occur in their respective alluvial transport system. Oh, now I have to undo the laser pointer. Okay, so I want to show you what that looks like here, and the title sort of gives away the goose. But on the x-axis here, we have that normalized distance metric. So on the left are rivers that occurred very close to their mountain front exit, and on the right are avulsions on rivers that occurred very close to the sink. The y-axis is just the percent occurrence, so you can read it as frequency or a histogram. But the thing to take away here is that we have this bimodal distribution of avulsion occurrence, right? So the vast majority are occurring right by that mountain front exit or right by the delta. And right, that is fundamentally interesting. I think it's intuitive to a lot of us, maybe that these are the places where avulsion occurs. But it was interesting to see this population, and particularly the background rate of avulsion being pretty low in between both right by the mountain front exit and right by the delta itself. I mean, 75% of all our data, our data set of avulsions occurred in these two places. And I want to sort of map this on. Sorry, hold on, I'm moving this Zoom thing. Yeah, and so why this is, right, is known. I mean, this is because sediment deposition occurs where you have a slope change or you get non-uniform flow effects of entering a standing body of water, right? This has sort of been shown by Brook et al. In this way, but this is a nice confirmation of this finding, and it sort of drives our intuition in the sense that fans are radial, right? They have a point source which distributes sediment. It's almost definitionally avulsive, and the same with deltas. It's a fan-shaped landform. I mean, we should maybe expect in a sample of avulsions for that to be the case. And that's sort of what I just talked about here. I want to just show you what I mean in the sense that we have fans, which are radial, deltas, which are radial, and in the middle, we have this coherent sort of meandering, and we do get a lot of movement, but avulsions are actually comparably rare in that sort of environment. Okay, so I wanted to motivate sort of the rest of this talk with this first portion, which is simply where do river avulsions occur in the source to sink system. What we found is that they're unequally distributed, and they normally occur right near the mountain front or shoreline. This is simply where much more comparatively sediment deposition occurs. So now, what are the conditions that favor river avulsion, that precede river avulsion? So one idea for why river avulsion initiates is called alluvial ridge superelevation. And I'm going to talk through that here. When you have an aggrading basin, and what that means is the bottom of the basin is dropping out, right, because of subsidence, and you're getting enough sort of sediment delivered to the basin that you can fill that accommodation. Well, that sedimentation rate decreases as you move away from the channels in the basin, right? And that happens, of course, because during flood stage, the fastest water is moving over the deepest part of the channel, and you get a gradient as you move towards the floodplain in that velocity where the water really isn't moving all that much. And what that causes is some shearing stress directed outwards, and that can loft sediment from the channel out onto the floodplain. But of course, because velocity is decreasing as you move into the floodplain, the sediment carrying capacity of the flow itself also drops. And so you get this decay signature of the sediment carrying capacity in the form of a levee or alluvial ridge, which is what I'm going to call it, which is this raised area next to the channel. So these alluvial ridges are built by differential sedimentation rates. But that can cause a little bit of a problem. When you are aggrading a channel above its floodplain, you're ratcheting up that water column and you're giving it a lot of potential energy. And we can quantify this potential energy with this idea of super elevation, which comes in the form of a ratio and two length scales. So the first length scale is going to be the height of the ridge above the floodplain. This tells you how perched the river is above the floodplain. And secondarily, we take the depth. So this tells us how dug in essentially the river is into the floodplain. And the idea here is that the ratio between the height of the ridge and the depth of the channel is this super elevation ratio called beta. And theory says that when beta or superelevation is above 1, meaning the bottom of the channel here is equal to the floodplain elevation, that we should expect an avulsion to occur. And there is good evidence to support alluvial ridge superelevation. I'm going to show you here two cross sections taken on the Indus River from data before the avulsion event occurred. In red here is the cross section taken right at the avulsion node. And what you can see here is that the bottom of the channel of the Indus is actually equal or a little bit above the elevation of the floodplain. So if you were standing on the floodplain of the Indus River, you would be looking up at the Indus itself, which is not a place that you want to be. And of course, it isn't just this example as evidence for super elevation. I don't have time to go into it, but a raft of work has been done looking at how channels super elevate themselves, both stratigraphically, experimentally, and numerically. But this is a fairly debated topic of what causes avulsion, and it wouldn't be that way if there was only one hypothesis. So there is another idea for why avulsions initiate, and that is called gradient advantage. And I'm going to return to this little cartoon to explain this. So to get an idea of gradient advantage, I'm going to define two slopes. The first is the downstream channel slope, just following along the river itself. And the second is the slope of the alluvial ridge, taken perpendicular to the channel, right? And so the ratio we can develop, called gamma, is the ridge slope, so that perpendicular side slope of the channel, over the channel slope itself. And that gives us an idea of simply the gradient advantage, or how much steeper these alluvial ridge slopes are compared to the channel itself. Now, theory says that when you have side slopes that are about 3 to 10 times steeper than the main channel, we should expect an avulsion. And that idea goes back further, but I'll sort of exemplify it with this model that was written about 26, 27 years ago at this point by Rudy Slingerland, that looked at the effect of the slope of the ridge compared to the channel itself. And so how he set this up is, if you look on this left figure here, you have a main channel. And that main channel has some slope, some flow, right? And it has some sediment concentration that varies from the bottom of the channel to the top of the channel. And then you have this crevasse channel that is sort of mirrored on this other side over here. But the crevasse channel has a certain slope itself. It has certain flow properties. And what the model asked is, basically, how steep does that ridge slope need to be for that crevasse to enlarge and capture all the flow of the main channel? And when does that sort of happen? So you can plot these two things. The first being the gradient advantage, that is how much steeper that ridge slope is than the main channel slope. And then what I would call more of the secondary effect, which is the height of this relative lip. And this just tells us how much of the crevasse channel can tap in to the main channel's flow, because sediment, there's more sediment concentration or higher sediment concentration at the bottom of the channel, the main channel, than the top of the flow of the main channel. But the thing to sort of realize here is simply that if you don't have a steep enough ridge slope in this crevasse channel, the avulsion will not occur. The crevasse channel will heal itself up and nothing will happen. But if that slope is steep enough for a given sort of lip height ratio, then we should expect a full avulsion to complete. So that's the idea of gradient advantage. And both of these get at something called the setup of river avulsion, right? So these two ideas for why avulsions may initiate, they get at this thing called the setup, because generally people think, people meaning folks that work in avulsion research, think that river avulsions need two things to happen. They need a setup, like I just said, but they also need what's called a trigger. So I'm gonna try to show that here with a fun little graph. So we just found out that avulsion potential can essentially be thought of as a function of beta, alluvial ridge superelevation, or gamma, gradient advantage. Okay, so that's what I'm gonna have on the y-axis. And on the x-axis is gonna be time. So Just imagine here that we have this little red ball, which effectively is our river system where an avulsion might happen. Now, the idea is when you have low setup, so you have low super elevation or low gradient advantage, we're at something called a stable equilibrium. We have a low avulsion potential. And so what that means is then that when we get a trigger, meaning any perturbative or catastrophic event that could possibly lead to a river avulsion, meaning floods or log jams, I mean earthquakes, animals, humans. Well, that can happen, but the river isn't going to avulse. It's too stable. It doesn't have enough of a gradient advantage or enough super elevation in order for that avulsion to occur. But if over time you get subsidence and aggradation, the longer term equilibrium conditions that eventually permit avulsion to occur, well, then you can achieve something called an unstable equilibrium, right? Where we have high avulsion potential. The river is going, it might even be experiencing floods, but it's in a sort of precarious situation. And so when a trigger comes around again, meaning a flood or a logjam, etc., well, then we go from an unstable equilibrium down to a stable equilibrium. And that process is avulsion itself. So because triggers are stochastic and they happen all the time, what is generally discussed and what I'm going to be discussing today is the setup or that development of the conditions that allow avulsion to occur. So these two ideas about river avulsion setup are sort of formally, they're maybe more like 30, 40, but the ideas, the generative ideas that go back to them are around 80 years old. I mean, you can trace a lot of them back to Fisk. But they're challenging to evaluate as elevation models generally and historically have obscured near river topography. So the first global digital elevation model of high resolution, more or less, that we as a scientific community were given was the Shuttle Radar Topography Mission, or SRTM DEM. And this was great because in 2001, they slapped a radar on the space shuttle, flew it around the Earth, covered, like I said, 80% of the globe, and gave us an idea of the elevation of the surface of the Earth. There is a problem in the sense that radar waves don't do a great job when you have dense riparian vegetation or standing water. And so what would happen is that in these vegetated regions, well, the heights of the land would look more like the heights of the canopy or some average between them. And there was just too much noise to resolve the actual alluvial topography in these river corridors, specifically vegetated river corridors. And there is a solution to this, right? LiDAR. And LiDAR we might all maybe be a little bit familiar with in the sense that it shoots billions, trillions of photons down to the surface of the Earth. Some of those photons hit the ground, some of them hit the trees, the canopy, in the same way as the radar waves do. But fundamentally, we have so many individual photons being shot out and returned that we can get something called a full waveform, meaning that we can get an idea of the distance from the LiDAR sensor down to the surface of the Earth, down to the trees, down to the canopy of the trees, and we can remove the vegetation and create things called bare earth DEMs because some of those photons just slip through the trees and the leaves. Now, this is great, but as many of you probably know, LiDAR is logistically difficult, it's expensive, and it certainly isn't globally covered, right? Only now are we getting um, a USA sort of LiDAR DEM, and even then it's time transgressive and all these things. I mean, it's just complicated to have full coverage LiDAR. So we needed something that would split the difference between these two approaches. And in 2018, NASA gave us this. They launched a LiDAR satellite called ICESat-2. And like I say here, they inadvertently created the perfect river profiling tool. And really what I'm talking about is that ICESat-2 was conceived to measure the ice height at the poles. So trying to tell us just how much ice we're losing as a result of climate change. But because the poles are on either side of the Earth, the satellite has to go from south to north. And in doing so, it covers much of the rest of the Earth. And when you have a river oriented perpendicular enough to that track, these little green tracks you can see right here, well, we can get a pretty nice river profile in bare Earth. And that's because ISAT-2 is really just a remarkable instrument. It's got this on-the-ground photon spacing of 70 centimeters, meaning that if it was flying over a football field, it would give you an elevation recording in between each yard line. I guess I realize now that's an American sort of reference, but still, it's got a very fine spatial resolution. And of course, this is nominal, meaning that if you have clouds or you have really 95% dense vegetation, it can be a little bit less precise than that. But in general, it's quite good. So I'm going to show you what these data look like now. On the right here, I'm showing you an image of a river on a lake in northwestern Turkey. An avulsion occurred about a decade before this ISAT track that you can see from A to A prime was taken. And what's great about this instrument is that not always, but sometimes you do get these really nice perpendicular profiles going across the river itself. And in this case, that white star indicates where an avulsion occurred. And so we have a reading right just about right upstream or right at of the avulsion node itself, about a decade after it occurred. So this is what the data look like. On the x-axis here, we have distance along track from A to A prime. And on the y-axis, we have the photon elevation from ISAT-2. In white are the ground photons, meaning these photons were classified as being associated with the ground by the ISAT-2 algorithm. And vegetation in green, likewise, was classified as vegetation. And when we saw this, we were really excited because this is an alluvial ridge, right? This is what we have been looking at, and we're seeing it beneath all this vegetation. And so what we can do is we can strip away the vegetation itself, and we can start measuring the parameters of super elevation and gradient advantage. So that's what we did. We can take the alluvial ridge height and we can divide it by the depth of the channel. Notice here that we don't actually resolve the true depth of the channel, right? ISAT-2 can't see through that river water. It's quite muddy, it's quite turbulent. And so we get an idea, we only get a reflection of the water surface itself. So we had to estimate channel depth. Here it just says machine learning. Don't have time to go into it fully today, but effectively you can think of it as we use the power law relation between discharge and depth, and we constrained that measurement with measurements of width and of slope. So it's essentially hydraulic geometry, but using width and slope to sort of inform the guesses a little bit more. But essentially hydraulic geometry is the estimate. So here we get a value of 0.4. Remember that the critical value was 1 for super elevation. We can also measure the gradient advantage, right? So this is the slope of the alluvial ridge over the channel slope itself. In this case, it happens to be about 9, which is pretty high, much steeper levees or side slopes than you have of the main channel slope. So we were able to do this for 58 out of our 174 rivers. This is because you have data issues with perpendicularity, with clouds, etc. But 58 we were pretty happy with. And so I want to show you what the data looks like here. I'm showing you two histograms. On top is super elevation or beta. On bottom is gradient advantage or gamma. In both of these plots, pink represents our data. The black line represents the median of our data for super elevation or gradient advantage. And then in gray is the theoretical values, right? From literature, Rudy Slingland's model that I told you about, other studies on super elevation. And so we hit in there pretty well. But what about from source to sink? So here I'm bringing back these three pretty broad categories based on geomorphology. These are the fans that happen at the beginning of the transport system, the alluvial plain rivers in the middle, and then of course our deltaic rivers at the end of the transport system. What you'll notice is that for super elevation, We have very high values for fans, a mean value of over 2. Remember, the theoretical value is 1. But as you move down the transport system towards alluvial plains and deltaic rivers, that value drops. We go from zero point 0.7 to 0.4. But when you look at the gradient advantage, you see something opposite. You have very low gradient advantage values for fans, meaning that the side slope of rivers on fans is generally not even about twice as steep as the main channel's slope itself. But by the time you get to alluvial plain rivers and deltaic rivers, further down the transport system, you see much higher gradient advantage, meaning you have much higher side slopes, or steeper side slopes, excuse me, than the main channel slope. Now I'm going to show you this same relationship in a different way in this next plot. On the x-axis, you can read this as relative source to sink position. Effectively, what this x-axis is our normalized distance metric divided by slope. What that gives us is it allows us to control not only for how long a given transport system is, but how big the basin is that the transport system is in. And you can read the axis as on the left, near sort of low values, are avulsions that occurred in proximal settings, so very close to the mountain front exit, and they're very steep settings. And then all the way on the other side, where you get to, excuse me, distal and gentle rivers. On the right side, these are avulsions that happen in really distal domains, so very far from the mountain front exit, and they're very gentle, so not a lot of background slope. And what you can see is we have a similar formulation in the sense that fans have high super elevation but low gradient advantage, and deltas have a low super elevation but high gradient advantage. And this is fundamentally strange, right? Both of these metrics are purported to indicate the likelihood of the same event, which is avulsion, but they're scaling opposite to each other in this space. So the data are seemingly suggesting that these two metrics are showing an inverse relationship. And I think I can break that down simply through shear stress, right? Of course, just a quick reminder, right? Shear stress, taking some assumptions, can be approximated with 4 terms: density, gravity, the depth of the slope, the depth of the flow, and the slope of the flow. I'm going to skip through a little bit of this since shear stress is something many of us probably understand well. Right, but this is what causes erosion to occur. We have some water moving with some velocity. It's got mass. It can then, therefore, it has momentum. It can transfer that to the grains and they move downstream. So I'm going to use this concept of shear stress to assert a hypothesis. And the hypothesis here is that the shear stress on the flank of the alluvial ridge, so moving down it during flood, for example, well, it must be equal to or greater than the shear stress in the current channel for an avulsion to occur, right? And that just simply means that the main channel here is experiencing some push on its bed and its banks from the river water. And for that water to get out of the channel in any way, well, it has to exert a larger push on the bed and the banks than it normally does. I can set this up as an inequality, showing that the shear stress down the alluvial ridge has to be greater than or equal to the shear stress in the main channel. You can break that down to the depth slope product, cancel out some things, do some algebra, move this product over, and then of course we have a blank on the side of the inequality. I'm going to put a constant there, lambda, simply because it looks like an alluvial ridge. And what you'll notice on the right side now is we have the product of 2 ratios. And those ratios we have actually seen before. They're the definition of alluvial ridge superelevation and gradient advantage, and they appear together in a product that has to be greater than or equal to some constant value, lambda. Now, what this indicates is that avulsion initiation might be determined not just by super elevation or gradient advantage, but by their combination, by their multiplicative combination. And that indicates to us is that for a constant value of that value lambda, we should expect to recover an inverse relationship between beta and gamma, between alluvial ridge superelevation and gradient advantage. And we can actually test that here. So on the y-axis, we have beta, gradient, or excuse me, on the y-axis, we have beta, alluvial ridge super elevation. On the x-axis, we have gamma or gradient advantage. And what you'll notice from all our rivers is that we recover this nice inverse relationship that is best described by a constant lambda value of 2. And that allows us to approach a sort of conclusion here, which is that simply taking some assumptions, for a river to avulse, the shear stress exerted on the avulsion pathway has to be about twice that of the shear stress exerted in the main channel. So we talked about the conditions that favor river avulsion. Remember, we had these two terms, these two metrics, super elevation and gradient advantage, that are supposed to indicate the likelihood of the same event. Turns out they're inversely related, which is interesting. In fans, super elevation is high, but in deltas, super elevation is low, vice versa for gradient advantage. And avulsions occur when the product of those two terms seems to be about 2, with a decent amount of scatter around that. So finally, I wanted to talk about when an avulsion occurs, where does it go, and how does it get there? So I'm going to bring back another, sorry, I got to move this thing again. So I'm going to bring back another video here. This is the Rio Serrare. It's in Colombia, and it underwent an avulsion. But before I show you the avulsion, I want to sort of talk about this problem, which is that if we know where the avulsion is going to occur, how do we know? No, video, wrong. How do we know where it's going to go? For example, when this river avulses, it could go and tribute down to the larger channel downstream. It could go perpendicular and find some local floodplain lake or a low. It could even do a hop, skip, and a jump and just go back to the same channel. So let's watch what it does. Okay, so the avulsion breaks out. And then it does this weird thing. It takes a turn to the south, takes a couple left turns, and then ends up in the same place it was trying to get to eventually. This does a good job showing, I think, just how these low gradient, highly morphodynamic systems can violate some of your intuition when it comes to flow downhill physics, right? I mean, of course, that is still applying here, but it's such a complex setting that normal flows can be sort of changed. Okay, so now what we want to do is come up with a model or a reason, a mechanism for where this river is going to go. Can we predict it if we know where the river avulsion is going to occur beforehand? So I think yes, and we're going to walk through a little derivation right now. So firstly, this is a toy digital elevation model. It's very vertically exaggerated. Here are the elevation values. And this is generally how I think about the Earth, right, as a sort of raster with pixels of different sizes. And I want to point out this star that might be hard to see on this brown block up there. That is going to represent the river, essentially, itself. This is going to be a probabilistic model. So it's effectively going to be a weighted random walk. And it's based on the idea that if avulsions are determined by the ratio of shear stresses in their pathways, well, maybe their pathfinding or where they go after an avulsion occurs is also governed by shear stress, by maximization of that shear stress. How much can the river really energy can it exert into the bed? So let's imagine we have a river that avulses. Generally, we can think of it as this star here. And so at t equals 0, the levee breaches. And at t equals 1, the river has decided, in some ways, I'm using decided in scare quotes there, the river has gone from this position on the brown block to the central position on the DEM. Now, the question is, where is it going to go next? And I think we can come up with a representation of a river that can answer this question. And I think that we only need two sort of terms here, which is slope dependency and inherited flow inertia. So what I'm saying is that river pathfinding, where a river goes on the surface of the earth when there's no channel, is a function of purely slope dependency and the flow inertia inherited from upstream. So I'm gonna walk us through this now. Slope I'm gonna represent in red, inertia in blue. And simply, the first thing we need to do if we want to get an idea of the slope around our river here is to calculate it. This is a digital elevation model. We can simply take the derivative and find the slope. And what I want to show you here is that slope acts as a nice score for us with how attractive it is to move to a different location. So, for example, on these gray blocks to sort of let's say, into the screen, they have slope values of negative 3.5, where negative is uphill in this convention. And you can read that as essentially it's very unattractive proposition for this river to go uphill. Whereas the downhill directions all have positive scores. And so we can start to represent this mathematically, the favorability of moving to any specific next position with slope. But the other thing is inertia. Now, slope is pretty easy to conceive of on a DEM. You just, like I said, take the derivative. Inertia is a little bit more complicated. But what I'm going to do is steal from the machine learning folks and use something called cosine similarity. Now, cosine similarity essentially tells us the, the degree of alignment between two vectors. So since we know where we came from, our last position was on this brown block. We can calculate the cosine similarity or the degree of alignment between the vectors from that position and future positions. So, for example, if we kept the same azimuth, if we kept following the same direction as we did in the last time step, well, then the cosine similarity value is close to 1. And that's because these vectors are just aligned with each other. But if the river goes perpendicular to that last direction, well, then those vectors are orthogonal and you get a value of 0.5. And so this does a nice job of representing the favorability of choosing a new direction, right? So you can imagine if you go directly behind, if you go upstream, essentially, you get a very low cosine similarity value because those vectors are really not aligned much at all. Okay, then we want to be able to modify these two terms, right? So maybe I want slope to matter more, maybe I want inertia to matter more. So we do have some modifying parameters. I'm just going to set these to 1 for now. And then we have to blend these two terms together. We have a representation of slope, we have a representation of inertia. I'm combining them here in natural language, right, with and, but I need to do it mathematically. So I need these blending parameters, or just a blending parameter, which you can think of this as an average, right, for now. So we're combining these two terms. And what that gives us is a combined influence score, meaning some representation of how attractive it is a proposition to move from that central location to any of the other locations. So this raw weight is essentially what we're looking for. We want to know what the probability is of moving from a central location to any other location. But we have a problem. I said probability, but the sum of these scores is negative. That, I mean, just logically doesn't make any sense. So we can't say anything about what's the probability of movement from this central position to any of these other positions unless we have a valid probability distribution that represents those sort of favorability of changing location. So I'm going to go back to the well and I'm going to steal from the machine learning people again. And I'm going to use something called the softmax function. Now, the softmax function has a really nice property in that it takes a vector of discrete choices, like our raw scores here in green, and it transforms them into a valid probability distribution from 0 to 1. And that's really nice for us because when we do that, you can see that negative values, those uphill values that are, basically upstream, they have low positive probabilities of movement, right? We can read these as probabilities now. But on this dark blue block, that actually has a fairly high probability of the river moving there in the next time step. And that's because it's generally in the same direction, and it's also lower elevation, right? So it's going to take advantage of that slope. So the highest probability is for the river or the random walker to go to that location. Now that's one step of the model. Of course, we have to run that now a lot of times, an arbitrarily large amount to come up with a path. So I'm going to show you that here. I just want to do a quick check on time. How we doing, UA, on time? I just don't have access to a clock here.
Yeah, so I think if you can finish it within a few minutes, that's perfect.
Okay, perfect. No
Yeah.
problem. Okay, so this is right. This is the last thing. So what we can do here now is test this because we have a well, let me back up here. So what I'm showing you here is a digital elevation model of the Rio Zulia, and it's in Venezuela. And the important thing about Rio Zulia is that it underwent an avulsion event in 2022, but this digital elevation information is from 2013. So we know where the avulsion occurred, this red dot on the screen here, and we also have the topographic information from before the avulsion occurred, meaning we can test our avulsion pathfinding model on this DEM. Okay, so we can run the model once. You can see this pathway here. Darker colors mean that the walker or the river has been to that pixel location more often. Lighter colors mean less often. And of course, if it's not colored at all, the walker has never been there. So we can run this once, twice, 3 times, 4 times, eventually something like 100 times, and you get this probability distribution of visitation, meaning that this is the probability that the walker or the river, the avulsing flow, was at that location. And now I'm going to overlay that on the avulsion event here. This is the large progradational splay that occurred in 2022. And as I overlay these two things, you'll notice that while we don't agree everywhere, right, we do get some important misses, we do a pretty good job of showing where this evulsive event is going to occur before it even happens. And we weren't able to do this, like I said, with all 58 of the avulsion data points that we had, but we did find 8 other locations where we had topographic information from before the avulsion occurred. Now, this is ranging from SRTM data, so that sort of noisier data, all the way to the DEM that we used in part of this work, or FAB DEM, which is an error-treated version of the Copernicus DEM. And similar thing here, these paths show the probability of visitation of the model. The white stars are where the avulsion itself occurred, and the blue is the river itself. And in black here is the true avulsion pathways. So this is where the rivers went after they avulse in reality. And what you'll see is that, again, we don't score everywhere. We get some misfires, but largely we do a good job of defining the avulsion corridors on topography data from before the event occurred. Okay, so these simple, when an avulsion occurs, where does it go and how does it get there? Well, this simple probabilistic sort of model that's essentially sensitive to slope and inertia does a good job of predicting avulsion pathways. Although more avulsion, this sounds kind of dark, but you know what I mean. Like we need more examples are needed to test the avulsion model, not more avulsions are needed. Um, so I'm just going to sort of move through this and I'll end up on the summary slide here and I'll stop there, UA.
All right, thank you, Jake. I mean, this is so cool to see everything being united, different factors be considered, and you can even predict where the version could go. So before anyone asks a question in the chat, I can ask one. I have seen that you show most of the versions happen either on the fans or in the dollars, but in most time, yes, I think those are mostly distributory multi-thread channels. But in most images, you show a single thread channel. So I would ask, what's the difference when the platform is making a difference to your avulsion rule finding? Could you make a comment on that? Yeah.
Yeah, I mean it's a great point. I would say that like the reason why I show more of the single thread avulsions is A, they happen to be more dramatic. And I think so, just from a visualization standpoint. And B, I think they sort of drive the intuition of the process really well because you can see the floodplain in between and that sort of thing. So, but as far as the plan form sort of affecting the avulsion model, especially the pathfinding model, maybe, is that in these, since we're working with digital elevation data that is a little bit older, when you have some of these more active rivers, particularly the braided rivers, particularly the fans, we could expect a decent, I mean, it depends on the system, but you could expect a decent amount of reworking there, and in that sort of sense. So we are limited by sort of topographic data that we have, but in terms of the gradient advantage versus super elevation model, I think that is simple enough that it can work agnostically to this sort of situation, the amount of channels, and that's a hindrance and a benefit in some ways, depending on the scale of analysis.
Cool. Okay.
Thank you.
So I can read the first one, and Lauren can read the next one.
Yeah.
So we have a question. Yeah, of course, there are many positive feedback. There's one question from Peter. What is the weighting between slope and inertia for avulsion paths? I think you mentioned this omega thing. You didn't talk about the value
Yeah,
of the weight. Yeah.
yeah, it's great question. And we did not do very many sensitivity analysis for this. I mean, effectively, what it is that slope has a 5 times higher weight than inertia. And I will just say that like that is some, so basically that is something that I'm trying to work on sort of now is the true sensitivity of this. But I will say is that when you do it with only slope, you don't get as good of a result, meaning that if you actually look at the amount of times that the avulsion pathway is covered by high probability Walker locations, that you don't get as good of an overlap when you use only inertia or only slope, but it does appear that slope is the dominant weight here. Absolutely. And that is something that, I mean, sort of I'll just go quickly on this, which is to say that I think something like this, those parameters, I think that they could be trained in a certain way in the sense that they might change based on certain topographies or maybe not, but it's enough of a high dimensional space that, we sort of did some light sensitivity testing, found that this worked, but it wasn't in scope to do the full parameter sweep, but that is something I'm trying to do. So I think I'm trying to answer that second question there too about the sensitivity of the different weights. But yeah, slope does matter more.
Yeah, and I think there was another question on this topic as well. And then last question maybe, what is the impact of other factors like vegetation and hydraulic roughness? And I think that's a pretty cool question for like mountain environments, for example.
Yeah. So again, these are things that particularly I will say that so to fully answer your question, not give like a political answer in some way. I don't know. Certainly they would affect it probably maybe even a decent amount. Things like cohesion too. So the grain size at play, I think could affect that lambda value. So that sort of constant value that represents the geometry, that critical threshold geometry. Now, there is a decent amount of variability on there. I will say that the median value is pretty robust at around 2, but there is a decent amount of variability on either side, and I think that could be collapsed one through grain size for cohesion effects, and two through vegetation, because I think vegetation has a pretty big effect on it stabilizing the sort of levee and ridge system, right? But also the hydrodynamics at play. And again, we take a steady state assumption, so we're looking at setup, we're looking at the sort of longer term average here, and why we did that again simply is because doing an unsteady flow sort of simulation on all these locations is just intractable at this point. So that is the direction to go. And I do think that one of the benefits of this being quite a simple model is that it can be modularized and added onto, right? So you could parameterize it with curvature, you could parameterize it with cohesion. It's sort of a framework that you can build upon, I think, and that's what I'm trying to do.
Okay, thank you.
Cool. So I think 2 questions from Alexandra and Emma have been answered. Then we have a question from Reju. He asked how this model could be applied for different regions of the world. like mountain channel, arid regions, and others?
Yeah, so I think that so what I just said talks to a little bit about that, but to answer your question about arid locations, and this is sort of just for funsies, but I think that the groundwater infiltration story here in these arid settings is a bigger deal than how I'm treating it, which is not at all. Um, and I think that I think that something like that, like which portion of the flow is sort of, directed into groundwater in the arid setting in particular, because when you see in flumes, when you see avulsions happen in flumes, even these sort of M river stream table flumes, it's all because they're losing competency through groundwater exfiltration, and so I do think that in arid environments, particularly arid environments that are like fans with these bigger grains where the water just has no hope of staying in the channel sometimes. It could look a little bit different there. But ideally, it should just change that lambda value because this is just a shear stress ratio, essentially. So if you can calculate those shear stresses a little bit more accurately than I did, then I think it could give you a better answer. But yeah, it's a great question.
And then the last question we have in stock is, do you have like avulsions that you witnessed that did not align with the value rules that we have? And do you think there is a need for another rule for avulsion to explain those cases?
Yeah, so I think that so I think I would just go back to this variability in this lambda value, this constant value. There is a decent amount of variability. Again, confident in the sense that it sort of has a very nice median representation. The mean is not too far from the median, although it is log distributed. The place I would say that it is undetermined more generally would be the submarine settings. And that's something I'm working on actually with Kyle Straub right now. And I think one of his students. But the submarine setting, they have these huge levees. I mean, just massive. And the degree to which, basically they have super elevation values, right, of like 10 or like 8 or something like that. And folks have I mean, Zane Job has talked about how this is a density problem in the sense that you have a lower density contrast between the ambient fluid and the sort of turbidite flow. But in this formulation, the density and gravity drop out. Now that's because it's a steady state approximation. But I'm very interested to know whether the ratio of shear stresses in these submarine cases are anything similar, or whether we did take a little too many assumptions in removing density and gravity in the formulation. So that's where I think is where it's quite interesting. But otherwise, I would say it's probably flexible enough to accommodate most settings as long as you parameterize certain things effectively.
Okay, thank you.
Yes, great. Okay. We don't have more questions in the chat, but I was just thinking, so I would foresee there's a great potential to integrate what you have found into future numerical models for photography, for landscape evolution, so for different areas, because now most of the process-based models haven't considered these factors in. I mean, so as far as I know. So I would foresee there's a lot of opportunities in the coming years. Yeah.
Yeah, I hope so. I think so too, and I think just I'll say as the data gets better, as our remote sensing and altimetric data gets better, we're just going to be able to be more precise in our formulations, which will get us closer to that UA. Yeah.
Yeah, yeah. Okay. So we have question from some person in the chat, but they ask for the slides. So this will be posted on our YouTube channel. Okay. So I didn't see any more questions, and we are just okay with time. So if it's okay for everyone, we are going to end this session. And thanks a lot, Jake, for your fantastic talk. And thanks for everyone to attend this talk. So we'll hopefully see you next week.
Great.
Yeah.
Thanks, everyone.
Bye, guys.
Next week's nothing.
Oh, not next week. Okay, I'll just stop recording.